Welcome back, everyone. Today, we are going to start section 7.3, which is trigonometric substitution. We will be using all the skills that we learned with the trigonometric manipulation from last time. I wanted to start, the heart of what we're doing today is from the Pythagorean theorem. And I wanted to recall that the Pythagorean theorem is leg squared plus leg squared equals the hypotenuse squared. And there's a couple of different ways that we can rewrite this. One of them is I can say that C is the square root. We're going to assume A, B, and C are all positive in this case. And you'll notice when the hypotenuse is all by itself like this, it's plus in between. However, if I want to solve for A or B, and I can subtract a B squared, you'll notice squared, C squared minus B squared. So A, or one of the legs, is equal to the square root. Now, we got to be careful here. With this one, it's plus because this is the hypotenuse. Notice when it's one of the legs, it's the hypotenuse squared minus the other leg squared. That's going to be really important. In fact, what we can do is rewrite our triangle even. Like this. So this is C, B, and instead of A, we can write it as square root of C squared minus B squared. Similarly, for this one, we can rewrite the hypotenuse and then here we can have the square root of A squared plus B squared. And that really is going to be the heart of what we're doing today, is trying to identify whether our sum of squares or difference of squares, depending on what we're doing, is going to fall on a leg or a hypotenuse. And then identifying if it is a leg, the hypotenuse is going to be the positive part minus the leg squared. So with that said, let's try to put everything together now. When we run into an integral like this, we can see we have a difference of squares here under the radical. And that's no problem. What we're going to do is we're going to use a triangle, that's the game plan, to come up with an alternative way of writing it in terms of theta now. Now I'm going to notice because it's minus, that means that this hypotenuse is 3, because 3 squared is 9. Then one of the legs is x. And then I'm now going to rewrite it like this. This is now the square root of 9 minus x squared. Notice it's the hypotenuse squared minus the leg squared. And what that does for us is it allows us to transform it from in terms of x's into terms of thetas. So I'm going to see that the sine of theta is the opposite, x over the hypotenuse, which is 3, which means x is equal to 3 times the sine of theta. Now there are 3 parts here that I need to transform. The one that's easy to forget is the dx, so I'm going to get that right away. So the dx is going to get replaced with that. I'm also going to notice that I can square the x. So there's my second piece, my x squared in the denominator there. Now I'm going to want to compare the square root of 9 minus x squared to the constant, which is the 3 in this case. And if you notice, that's going to be the adjacent over the hypotenuse. This means that cosine of theta is the square root of 9 minus x squared over 3, which means the square root of 9 minus x squared is 3 cosine theta. And so here are my big players. So here transforms the dx, here transforms the denominator x squared, and here transforms the numerator. And I'm going to piece all of that together to get the integral of 3 cosine theta over x squared, which is 9 sine squared theta, dx, which is the 3 cosine theta d theta. And now we've done a complete transformation from x into theta. And I'm going to notice that the 3 and the 3 and the 9 are gone. And I'm actually going to end up with the integral of cosine squared theta over sine squared theta, d theta, which is the integral of cotangent squared. And now my trig manipulation skills come into play. This becomes the integral of cosecant squared theta minus 1 d theta. Integral of cosecant squared is going to be negative cotangent theta minus theta plus c. Now you'll notice we're still in terms of theta. And what I'm going to do for the theta by itself, I'm going to transform this into theta is inverse sine of x over 3. Cotangent, I'm going to go to the triangle. Cotangent is the adjacent over the opposite. So this transforms into the adjacent, so negative square root 9 minus x squared over the opposite, which is x, minus theta, which is the inverse sine of x over 3 plus c. All right, so that is trig substitution. Let's move on to number 2. So for this one, we are going to find the area of an ellipse. If you recall, an ellipse centered at the origin looks like this. Where A is the how far from the origin we go in the x direction, and B is how far we go in the y direction, up and down. And what we're going to do is we're going to get y squared by itself. So this becomes y squared over b squared equals 1 minus x squared over a squared. Multiply the b squared over. And we're going to do a little manipulation here. Let's go down here. I'm going to get a common denominator here. And now when I do the square root, and we're just going to deal with the top half of it. Actually, what we're going to do is I'll show you in just a second. So when I do the square root, the b squared and the a squared just become b over a. And then I end up with this here. And to be clear, what I'm going to do with this ellipse, this is A, this is B, I'm going to find just the area of a fourth of it. And then at the end, I'm going to multiply times 4, and then that'll get the whole, because it's ellipses are so symmetric. All right, and this of course is negative A, and this is negative B. So what I'm going to do is I'm going to integrate from 0 to A, and again, this function is y, this y here. So to find the area, I'm going to go 4 times, I'm going to pull the b over a out because they're constants. The integral from 0 to a, and the square root of a squared minus x squared dx. All right, so let's set up a triangle and get our information. And it looks like we once again have a subtraction. So our hypotenuse is a in this case. Our side is x, which makes the square root of a squared minus x squared, the other leg. Once again, this means that the sine of theta is x over a, which means x is a sine theta, which makes dx a cosine theta, d theta. So there's one of my pieces. There's my dx, and then I now need to get that. That, once again, the a is a constant, so I'm going to compare the adjacent to the hypotenuse. That's cosine. Which means the square root a squared minus x squared equals a cosine theta. So there's our other piece. So back to our problem over here. This becomes 4b over a. The integral, that is a cosine theta times our dx times a cosine theta d theta. And I'm going to hold off on the boundaries for now. When we get back to in terms of x, then I'll plug those in. What we could do is plug in for 0. Plug in 0 for x here, and then so the sine of theta equals 0. And then we can plug in a there, and that would make that 1. Actually, let's do a full transformation on that. So when x equals 0, sine, that's going to be, theta is going to be 0. And when x equals a, that means sine of theta equals 1. That's at pi over 2. And we can see that one of the a's reduce out here. I have another one here. So this is going to become 4ab. The integral from 0 to pi over 2 of cosine squared theta, d theta. And if you recall, we have a trig manipulation property for that. It has a 1/2, so I'm going to actually cut that in half. So that's going to be 2ab, integral from 0 to pi over 2 of 1 plus cosine of 2 theta d theta. This becomes 2ab theta from 0 to pi over 2 plus, and I'm going to get an extra 1/2 from that there, and that's going to cancel out there. So this is just ab sine of 2 theta from 0 to pi over 2. Now the nice thing is, when I plug in pi over 2, that gives me sine of pi, which is 0. And when I plug in 0 here, sine of 0 is also 0. So this whole piece right here goes to 0. And this down here becomes 2ab pi over 2 minus 0, right? When I plug that in. So this whole thing is just pi ab, which is cool. That means that the area of any ellipse that is centered at the origin is going to have an area of pi times a times b. Kind of cool. All right, let's move on to the next problem, which is the next page. All right, you'll notice this one has a plus. The other two that we just did had a minus. So let's set up our triangle. Remember, when it's plus in between, that means the radical is on the hypotenuse. Make sure you identify your theta. That's important. So there's our triangle that we're going to work with. In this case, we're dealing with tangent. By the way, if you switch those two, then we'll be dealing with cotangent, which is okay too. All right, so my first piece I need to get is the dx. I'm going to need x squared as well. And so I'm just going to literally square that. And now I need to compare the radical again to the constant. So that's going to be the hypotenuse over the adjacent. That is secant theta. Which means radical x squared plus 4 equals 2 secant theta. So there are my three pieces once again. So these two here, as well as this one, to completely transform my integral into terms of theta. So the integral of 1 over x squared, which is here, 4 tangent squared. Also, the radical is down there, so that's going to be times 2 secant theta. Times my dx. Again, it's easy to forget that dx. It's right there, 2 secant squared. D theta. So there we are. And what's going to make this a lot easier to deal with is, first of all, do you see the 2's are going to reduce here? The 2 and the 2, and I'm going to be left with a 4th, which I'm going to pull to the outside of the integral. And one of the secants also reduces out. That, when I bring that up, becomes cotangent squared. And times secant theta, d theta. One of them again reduces. And now I'm going to break everything in terms of sine and cosine. That's going to make it easier to see what reduces out and what doesn't. So this is cosine squared theta over sine squared theta times 1 over cosine theta d theta. And we can see one of the cosines will reduce. And that actually is going to give me, well, two things we can do. I can do a substitution, let u be sine of theta, or I could break it into cosine over sine, which is cotangent, and then 1 over sine is cosecant. And let's just do a substitution, keep it simple. And you can see the derivative there. All right, so we have two transformations here. We have into theta and then into u. And so now we're going to have to, at the end, go all the way back. This becomes 1/4 the integral of u to the negative second power du, which when we add 1 to the exponent and the whole deal, we end up with negative 1/4 u to the negative first plus c. And now we begin our journey back. So this becomes negative 1/4, 1 over 4u, I should say, where u is sine plus c, negative 1 over 4 sine of theta plus c. And let's make that -1/4 cosecant theta plus c. Cosecant, if I go back to my triangle, is the hypotenuse over the opposite. So this becomes -1/4 times the hypotenuse, square root x squared plus 4 over the opposite, which is x in this case, plus c. There you have it. You could write that as over 4x if you wanted to, but this is fine. So that's with a plus in between. And I'd like to move on to the next one. Notice my final answer has to be in terms of the original variable, which in this case was x. For this next one, we have options. I could set up a triangle, but I'm going to notice that instead of setting up a triangle, I can just do a direct substitution here because the derivative of what's under the radical is right there. So I'm going to let u equal x squared plus 4, and du equal 2x dx, which means 1/2 du equals x dx, which of course is right there and there. So why is this in the middle here? Well, sometimes you'll get going and you'll see that you want to set up a triangle, when in reality, you can use a different technique that's going to have things go a lot quicker. You can try doing this with the triangle. Again, that'll be on the hypotenuse because of the plus, to verify that you get the same answer. So here we have, there's the 1/2 there, the integral of 1/√u du. And let's keep going. 1/2 the integral of u to the -1/2 power du. 1/2 1/1 minus 1/2 u to the -1/2 plus 1 plus my constant. And all of that turns into, that becomes a 1/2, and the reciprocal of that is 2. This becomes u to the +1/2 power plus c. And u, once again, is x squared plus 4. Notice the 2's completely reduce out. So we end up with the square root of x squared plus 4 plus c. Nice and simple. We at least try. And let's move on to the next one. All right, so here we have a generic one. Now we have a subtract here. We started with subtract and it was sine. This one's going to be different because now the hypotenuse is the x. The constant in this case is going to be the a. So let's draw our triangle. So in this case, x is here. The leg here is square root of x squared minus a squared, and this of course is a. And I'm going to notice that the sine of theta is a over x. And if I solve for x, I'm going to end up with x equals a over sine theta. Or easier to write it as a cosecant theta. Our dx is going to be negative a cosecant theta cotangent theta d theta. And our denominator is going to be, I'm going to compare the adjacent leg to the opposite leg. That is cotangent. So cotangent of theta is the adjacent over the opposite, which is a. So the square root of x squared minus a squared equals a cotangent theta. So there are my two pieces that I need. The dx. I find the dx first because I find it the easiest thing to forget. So you may want to make a habit out of that yourself. And let's rewrite our integral. We're going to transform it. All right. Oops, that's a negative there. So I'm going to notice that the a's reduce out right here. The cotangents reduce out, and I'm just left with cosecant negative the integral of cosecant theta d theta, which is negative ln of absolute value of cosecant theta. I showed you these formulas in the last video, minus cotangent theta, absolute value plus c. Now we've done the integral, but we still need to transform this back into x. So let's be real careful as we do this. Negative ln absolute value. Cosecant is the hypotenuse over the opposite. So that's x over a. Minus, and cotangent is the adjacent over the opposite. And you could rewrite this as a single, because they already have a common denominator, or you could just stop there. Both work. And there you have that one. Let's move on to number 6 here. This one's going to be just a little bit different. All right, you'll notice this is a definite integral. Also, you'll notice we don't have a radical, but we'll take care of that in just a moment. Let's start with our triangle. Our triangle is going to be focused here. And this one we have a lot to transform. All right, so notice it's plus. So that makes this 2x, and this one 3, and this the square root of 4x squared plus 9. Now, you might be thinking to yourself, it doesn't say square root, it says to the 3 halves. That's true. We'll get there. All right, so let's start by digging our x out. I'm going to compare, this is going to be tangent. Theta is 2x over 3, which means x is 3 halves tangent theta, which means dx is 3 halves secant squared theta d theta. So there's our first piece. Our next piece is x to the 3rd power. So x to the 3rd power becomes, I'm just going to cube that, x cubed is 27 over 8 tangent to the 3rd theta. So there's our second piece. Now our third piece involves the radical. So I'm going to compare that to the adjacent. So the hypotenuse over the adjacent, that's secant theta. Over 3, which means 3 secant theta equals, and instead of calling it square root, I'm going to call this 4x squared plus 9 to the 1/2 power. And now what I'm going to do is I'm going to cube both sides, and that'll get me the 3/2 power like I need. And there are all the pieces that I need. There and there. Oops. Switch off the black here. So now I have the integral. I'll deal with the boundaries in a moment. X cubed, just 27 over 8, tangent cubed, theta, over 27 secant cubed theta, times my d theta, which is 3/2 secant squared. Ooh, let's try to piece all this together. All right, so we have the 27s are going to reduce out. That's going to become 1/8. Yeah, 1/8 times 3/2. And I'm going to notice 2 of the secants are gone. So I'm left with tangent cubed theta over secant theta, d theta. All right, I'm going to break everything into terms of sine and cosine just to make it a little bit easier. And notice I don't have the boundaries yet. I'll get there. This becomes sine cubed theta over cosine cubed theta times cosine theta. All right, looks like one of the cosines are going to reduce out. So sine cubed theta over cosine squared theta, d theta. All right, so now we're in business. Next. All right, so 3/16. And we end up with, let's write it like this. I'm going to save off one of the signs. And now I'm going to do a U sub. So let's do. All right. With 1 minus u squared over u squared du. So 3/16. Integral of 1 over u squared minus 1 du. With a negative. There. And I'm going to go ahead and integrate those. This is going to give us negative 1 over u minus u c. All right, and u is cosine. No, let's just put that down here. And this becomes negative 1 over u, which is cosine theta minus cosine theta plus c. 1 over cosine is secant, so I'm going to go all the way back to the triangle. So we're going to squeeze it in. Secant is the hypotenuse over the adjacent. Negative the hypotenuse, which is the square root of 4x squared plus 9 over the adjacent, which is 3, minus cosine, which is the reciprocal of that. 3 over square root of 4x squared plus 9. Oh, and there's no plus c. I forgot this is a definite integral. We'll get to that. And this is going to be evaluated as x goes from 0 to 3 root 3 over 2. All right. So now we got to do a little bit of arithmetic. Now what's funny about this one is when I plug in 3 root 3 over 2 into that x there, multiply it, or square it, multiply it times 4 plus 9, that's 36. So all of this becomes negative 6 over 3 minus 3 over 6. Now we're going to plug in the 0. It's plus because it's minus minus. Plug in the 0, so that's going to give me negative. That's gone. That's going to be a 3. That's going to square root of 9 is 3. So 3 over 3 minus 3 over 3. All right, let's clean this up. That becomes 2 minus a half. Negative 2 minus a half, that's negative 5 halves. It becomes negative 2. Negative, so negative. Now 2 times, that becomes 3/8. Let's clean all that up. So that becomes positive 15 over 32 minus 3/8. That's going to be 12 over 32, which gives us 3 over 32. Wow, that one was involved. All right. Whew. All right, so let's move on to example 7 here. And this is going to take us sort of in a new direction. All right, I need us to recall something called completing the square for this one. And that's going to involve taking that number 4 there, cutting it in half, and then squaring it. So let's do this. So I added a 4 and subtracted a 4, because half of 4 is 2. 2 squared is 4. This becomes x plus 2 squared, and that becomes plus 9. So keeping that in mind, I'm going to rewrite this like this. Now we do this when we cannot factor that denominator. If we are able to factor that denominator, then actually section 4 will tell us what to do with that. So even if it did factor, we wouldn't know what to do with it yet until the next lesson. All right, I now see a sum of 2 squares. You might see that you could do a shortcut with a tangent rule. I'm going to do a quick substitution, and then we'll transform it all the way back. So I'm going to let u equal x plus 2, which means du equals dx. So very quickly, we're going to end up with the integral of 1 over u squared plus 9 du. And again, you can see an inverse tangent rule there. We can recall this rule here, that the integral of 1 over x squared plus a squared dx is 1 over a inverse tangent of x over a plus c. But what I'm going to do is I'm going to set up the triangle to show you where that comes from. So red is the only color I have left. So I'm going to set up a triangle. And it's plus, which means, excuse me, and we can see that the tangent of theta is x over a, or that x equals a tangent theta. Dx is a secant squared theta d theta. And we can see that this, we can get the radical there by comparing it. That's going to be secant theta is the square root of x squared plus a squared. You might be saying to yourself, hey, there's no radical there. Don't worry, we'll get to that. Over a, which means a secant theta is equal to the square root of a squared, x squared plus a squared. And then when I square both sides to get rid of the radical, which is what I need, and these should all these x's should be u's, u, 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 u. And squaring that gives me a squared secant squared theta equals u squared plus a squared. All right. With all of that said, go back to here. This becomes the integral of 1 over, and there we are without the radical, that a squared secant squared theta times the d theta, du, which is here, the a secant squared theta d theta. And you'll note everything except the 1 over a. Oh, I did it. That's a 9. So the a is actually 3 in this case. So notice one of the a's reduce out, so I'm left with a 1/3. And notice that secant squareds are gone. All right, so we end up with 1/3 theta plus c. Now, I'm going to go back to here and say that theta is inverse tangent of u over a. Which is 3 in this case. And u, once again, is the x plus 2. So this is sort of why this works, but you can see a is 3, so it's 1 over 3, inverse tangent of u, in our case, which became x plus 2, over a, which is 3, plus c. So if you want to use a shortcut, you can. I wanted to show you why it works. And we are to our last problem. All right, here we go. What we need to do again is complete the square. And to do that, I'm going to actually use some scratch paper. So 3 minus 2x minus x squared. So I'm going to rearrange this just to make it easier. X squared plus 2x minus 3. And I'm going to note I'm going to add a 1 in there. Because half of 2 is 1, 1 squared is 1. So I'm going to rewrite that as this. That's going to save us a little work. All right. So 4 minus x plus 1 squared dx. And you can see I can set up a triangle based on this. I could do a quick use substitution and substitute, but I'm just going to leave it as is. And remember, this is from a previous problem. So let's set up our triangle. And the hypotenuse is going to be 2. One of the legs is x plus 1. And this becomes the square root of 4 minus x plus 1 squared, which means the sine theta is x plus 1 over 2, which means we get 2 times theta is x plus 1. All right. And then, so I need x by itself. So this gives me x equals 2 sine theta minus 1, means dx is 2 cosine theta d theta. All right, so there's one of my pieces. Two actually, because we need x as well. And now I need to compare the adjacent to the hypotenuse. So that's cosine of theta is the square root of 4 minus x plus 1 squared over 2, which means 2 cosine theta is the square root of 4 minus x plus 1 squared. So here are my main pieces. This is for the numerator. This is for the denominator. So let's do this. Integral of 2 sine theta minus 1 over 2 cosine theta times dx, which is 2 cosine theta d theta. And I'm going to notice the 2 cosine thetas are gone. And we just end up with 2 integrals. Oh, no, I'm sorry. 2 sine theta minus 1 d theta. And I can break that up into 2 distinct integrals. Straighten that out. This becomes negative 2 cosine theta minus theta plus c. Now, theta by itself is going to be inverse sine of that. And cosine is going to be the adjacent over the hypotenuse. So this is going to give us negative 2 times the adjacent, which is the square root of 4 minus x plus 1 squared over the hypotenuse, which is 2. Then minus inverse sine, so I'm getting that from here. Inverse sine of x plus 1 over 2 plus c. I'm going to notice the 2's reduce out there. And it looks like we end up with just negative. And I'm going to go back. So this is what's under the radical. I'm going to write it back to what it originally was. And in the end here, you don't have to do that, but I'm going to go ahead and choose to do that. So negative the square root of 3 minus 2x minus x squared, which is that, minus inverse sine of x plus 1 over 2 plus c. There you have it. Trig substitution. Crazy fun. Hope that helps.